A presentation on iron carbon equilibrium diagrams, in which the subtopic we are going to deal with is cooling, solidification of liquid, cooling curves, polymorphism, allotropy, and constituents of iron carbon system. Myself, M.Kiran Kumar, M.Tech, CL Mechanical Engineering, Government Polytechnic, Kataram. So, let us have a look about the topics just now we have discussed. So, the topics to be covered. So, as we have discussed, cooling, nothing but the solidification of liquid, cooling curves, polymorphism, allotropy, the constituents of iron carbon system. So now let us have a look over the cooling of a liquid metal. What happens? So the crystallization occurs around a small nuclei, which may be the impure particles, so as given here. But the first crystals which are having the crystal shape, the metal naturally solidifies. For example, FCC, nothing but face-centered cubic structure in case of copper metal. So we can say that the first crystals formed will be having the shape of naturally solidifying. So coming to the next, as the crystals goes on growing, it tends to develop spikes. Continuously developing spikes are developed, so which forms a tree-like of structure known as a dendrite. So crystallization, forming the first crystals, naturally solidifying, developing spikes known as dendrites. So this is the cooling of a liquid metal. Now let us enter into the what is dendrite growth. So just now we have discussed that this is the tree-like of structure. Whenever the liquid solidifies, it forms a dendrite or a tree having several branches type of structure. This is the growth of dendrites. So as the dendrites grows, the spaces between its arms fill up. Outward growth stops when growing arms meet others. Eventually, the entire liquid solidifies as there is little trace of original dendritic structure, only the grain into which the dendrites have grown. So, the spaces between the arms fill up, then arms meet the others, growing the dendrites, and then the liquid solidifies where little trace of original dendritic structure is available. So, whenever it is in the liquid condition, small nuclei act as centers for crystal growth. So, whenever the dendrites, so here the small dendrites begin to develop from the nuclei. So, from this, the nuclei, small dendrites are started developing. This is the dendrite formation. And these dendrites continue to grow with several branches here in this form. And next, coming to the fourth step, as the dendrites grow, the spaces between them fill in. So this is the spaces filling from the one dendrite to the other. So the solidification is complete, little evidence of the dendrite structure remains. So this is the total grain boundary having different dendrites combined. So this is the formation of nothing but the solidification of metal. So initially we have started with the liquid structure, liquid form, then small dendrites have been started. The dendrites continued to grow, and one dendrite connected with the other so that the spaces between them are filled, and finally the total grain boundary is formed, showing a little evidence of the dendrite structure. So now let us move to the thermal equilibrium diagram, what it is. When pure water is cooled at 0 degrees centigrade, nothing but it changes from liquid to solid, then we can call it as an ice. So the formation of ice. The cooling curve shows a plot of temperature against time down to 0 degrees centigrade. The water only exists in the liquid state. In 0 degrees centigrade, solidification start to occur. Nothing but the cooling curve is a plot or a graph generated between temperature and a time. Whenever the temperature of a metal is reduced to 0 degrees centigrade, where the water only exists in liquid state, at 0 degrees centigrade solidification starts. And while the process is going on, the temperature remains constant as the latent heat of fusion is lost. So let us have a look about the graph between time and the temperature, nothing but thermal equilibrium diagram. This is at 0 degrees centigrade and this is a liquid form. This is a solid form, liquid changing into solid. At 0 degrees centigrade, liquid plus solid. This is the thermal equilibrium. So this is the cooling curve generated between the time and the temperature. This is the temperature and this is during the time going on. The liquid changing from liquid state to solid state, nothing but the ice here. At 0 degrees centigrade, nothing but the thermal equilibrium, liquid plus solid is available. So now let us have a cooling curve for alloys. So the same temperature and the time. So the cooling curve for a particular composition. So here A to B composition, this is the cooling curve. And this becomes a liquid and this is a solid. So all pure substances show similar behavior with alloys. There is no single temperature plateau. And the range over which solidification occurs depends on the proportions of elements in the alloy. So nothing but most of the pure substances have the same behavior with the alloys, and the solidification range, nothing but the occurrence of the solidification depends upon the type of composition or proportions of the different elements in a particular alloy. So the points marked A and B in this previous graph as referred to as arrest points, and the temperatures at which they occur are known as arrest temperatures. So this is the, if this particular point at particular temperature known as arrest temperature A, arrest temperature B. So this is a arrest temperature A and arrest temperature B. cooling curve for a solid solution. So the same temperature and the time. Here, this is the equilibrium phase. Phase change start temperature, and here the phase change finishing temperature. So here up to here this is a liquid phase, and here it is a solid phase. So this is a cooling curve for a solid solution. So here, whenever we move in depth to this cooling curve of a solid solution, we have different temperatures known as lower critical temperature, abbreviated as LCT, and upper critical temperature, abbreviated as UCT, and TA, melting temperature of alloy A, and TB, melting temperature of alloy B. So here in this particular diagram, we are able to see clearly the same equilibrium type of diagram. Temperature, the graph is plotted between temperature and time, and here this particular point, at this particular point, LCT1, lower critical temperature 1, and above upper critical temperature, LCT2, UCT2, 3, lower critical temperature 3, lower critical temperature 4. Similarly concerned, upper critical temperature 4 and upper critical temperature 3, 2, 1. And whereas the melting temperature of B alloy, this is the melting temperature of A alloy. And observe here the percentages are being 0 to 100 from left to right, and 100 to 0, that is from left to right. So here, whenever we observe the phase diagram, depending upon the composition here, instead of time, we are going for the composition 0, 20, 40, 60, 80, and 100 is the temperature. So LCT1 and UCT1, LCT2, UCT2 both are on the same vertical line. LCT3 and UCT3, upper critical temperature 3 and lower critical temperature 3, both are on same line. Whereas similarly LCT4 and UCT4. So that is the difference between graph plotted between temperature time and the temperature composition. So coming to the composition percentage of B, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So here, these are the different compositions depending upon the temperature, and this is the time. So in the previous topics, we have discussed different cooling curves. Now let us move to the polymorphism. So what is polymorphism? Coming to the polymorphism, it is a physical phenomenon where a material may have more than one crystal structure. It is a physical phenomenon where a material may have more than one crystal structure. Whatever the crystal structure, that is more than one, known as polymorphism. So now next is allotropy. What is allotropy? A material which has polymorphism, nothing but a material that shows polymorphism, exists in more than one type of space lattice in the solid state. So if change in structure is reversible, then the polymorphic change is known as allotropy. Nothing but whatever the structure change is reversible. When it is a reversible process, we can call it as an allotropy. So next is the cooling curve for a pure iron. Cooling curve for pure iron, allotropic behavior of pure iron. So let us have a look over the graph plotted between temperature in Fahrenheit and the time. So here the temperatures are plotted as 1414, 1666, 2554, 2800. And here coming to the times, first at 1414 degrees Fahrenheit, the alpha iron BCC magnetic, and this particular alpha BCC alpha iron base centered cubic structure changes to alpha iron but non-magnetic type. Initially it was magnetic type, then later whenever the temperature goes on increasing from 1414 to 1666 Fahrenheit, then the magnetic alpha iron of base centered cubic structure changes to alpha iron base centered cubic structure of non-magnetic type. And still we are, whenever we go on increasing the temperature up to 2554, then the gamma iron of face centered cubic, which is of non-magnetic type, and then above this 2554 temperature up to 2900, then it is a delta iron of BCC structure, and above it is totally liquid, nothing but above 2800 degrees, nothing but 2800 Fahrenheit, it becomes liquid, nothing but liquid state. So here let us see the alpha iron, the structure. So here you can see the center atom, and then the sides 1, 2, 3, 4, 5, 6, 7, 8. So similarly we are able to see here this particular structure. So here also we are able to see the same. So variation in microstructure in steels, nothing but how the different phases occurs. Let us have a look. So here let us see the different structures and different phases of these particular microstructure in steels. So here let us start with the ferrite and perlite in the iron carbon equilibrium diagrams. So the ferrite and perlite combination is shown here in this form, ferrite and perlite. And this is the cementite plus perlite. This is the structure. And here it is austenite plus cementite. This is austenite, and this is austenite plus ferrite. We can have the change in the structure. And this is the austenite. So here 1.2% carbon is dissolved in a solid solution of FCC austenite, and this is the austenite. So the changes that occur in a 1.2% carbon alloy as it is cooled from 1000 degrees centigrade, let us have a look over here. So 1.2% carbon dissolved in a solid solution of FCC structure austenite. This is austenite, and this is the structure. And second is, as the cooling continues, the cementite soaks up the carbon until 723 degrees, and there is only the eutectide composition of carbon left, which changes to perlite. So here this changes to perlite. So thus this gives a steel containing cementite and layered structure perlite. So the allotropy of iron. The iron changes its structure whenever it is heated. The iron has the ability to exist as BCC or FCC depending upon the required temperature and several conditions. So this is the ability, this ability is known as allotropy of iron, nothing but the reversibility. So let us see the alpha, gamma and delta irons here. So from 0, alpha BCC structure forms. So from 0 to 200, 400, 600, 8 and 910. At 910 degrees, the iron is crystallized in BCC, base centered cubic structure form, which is called as alpha iron. So at 910 degrees centigrade, the iron is known as alpha iron. Whenever the heat, whenever it is continuously heated above 910 degrees centigrade up to 1000, 1200 and 1390 degrees centigrade, then the iron is a FCC, face-centered cubic structure known as gamma iron, and continuously heating from 1390 degrees centigrade to 1600 degrees centigrade, it again returns back to BCC, base-centered cubic. So whenever the temperatures are being changed, the structure from BCC to FCC and again from FCC to BCC, this is known as allotropic form. So initially at a 910 degrees centigrade, it forms ferrite with carbon, and then it changes from to austenite with carbon, finally forming ferrite with carbon at from 1390 to 1600 degrees centigrade. So this is known as the allotropic form of iron. Allotropy. Now so we were discussing the allotropy of iron. Now let us move to the ferrite, nothing but the alpha iron. So as we are discussing, it is a BCC crystalline form, nothing but base centered cubic crystalline form, which is a stable form of iron below 912 degrees centigrade. Only up to 0.02 percentage of carbon exists in this particular solution. So this is the body centered cubic structure. So here cubic packing sequence. So centered we're having the atoms connected the top and bottom. This is a body centered cubic structure. So this is a BC structure having 4 ends, again the bottom 4 ends and the centered atom. So BCC unit cell, what is a unit cell then? So here this is a unit cell. 4R is the calculation. So Now let us move to the austenite, nothing but gamma iron, which is a face-centered cubic structure which is having high formability, high solubility of carbon. So over 2% carbon can be dissolved in it. At 1148 degrees centigrade, most of the heat treatments begin with this particular single phase. So this is the face-centered cubic structure. Along the faces, along these faces, 1, 2, 3, 4, along each face, we have an atom that is known as face-centered cubic structure. So if this is one face, this is a red one atom, second face, third face, like that, 4 faces, we have all the sides and top, bottom, each and every face we have the atoms. So this is a FCC unit cell. So this is a representation along with the calculation part. So coming to the delta iron, this is a present at extreme temperatures 1492 degrees centigrade. Maximum carbon dissolved is 0.08 percentage. So that is the different types of irons. So now let us move to the cementite, which is known as iron carbide. So cementite is an iron carbide. So stoichiometric intermetallic compound, which is very hard, brittle, exact melting point is not known, but even its Curie point 770 degrees centigrade. So the atomic level non-magnetic to magnetic transition can be performed. So next we can move to the perlite. It is an intimate mixture of ferrite and cementite. Ferrite and cementite combination is known as perlite, and it has a distinct lamellar structure, consists of alternate layers of ferrite and cementite. So alternate layers of ferrite and cementite are arranged in a lamellar structure forming perlite. It is an eutectoid phase transformation of austenite at 723 degrees centigrade, having 0.83% of carbon. Nothing but in eutectoid phase transformation of austenite then forms perlite. So next is ledaberite. It is a mixture of austenite and cementite. It is obtained by eutectic phase transformation of a liquid alloy containing 4.3% of carbon, cooled below 1148 degrees centigrade. So below 723 degrees centigrade, ledaberite changes to perlite. So now let us have a look at the microstructures of iron carbon system at different compositions. Microstructures of iron carbon system at different compositions. So let us have a look. So these are the compositions and this is the temperature. So initially here at 20 degrees centigrade, 100% ferrite, almost pure form of iron. This is the structure of purest form of iron. So we can call it as an almost pure iron, not exact iron, but it is a 100% ferrite. This is the structure. So the second is here at 20 degrees centigrade only. This is perlite plus ferrite. Perlite plus ferrite composition. Here we are able to see the different changes in the structure. And next is, so perlite having darkest portion and blank portion is known as ferrite. Coming to the third, 100% perlite eutectoid phase. So here, so 100% perlite. So the perlites will be forming totally in the structure. Next is iron carbide and perlite. So this is the iron carbide having darkest structure along the borders of the perlite. The rest portion is perlite. So the next is slightly the above, so moving from 3%, forms iron carbide plus perlite. Here the darkest structures, the darkest borders of the perlite. So this is the different compositions of iron and the iron carbon equilibrium diagram. So these are the topics covered. Now let us have a summary of the topics covered in this particular presentation. So in this particular topic, this particular presentation, we have started with the cooling of a liquid metal, how the solidification process continues. So how the solidification starts naturally and how the dendrites are formed, how the dendrite structure, like a branches of a tree, how the dendrites are grown. So the dendrite growth also we have discussed in this particular diagram. These are the dendrites, just like a tree branches, they appear. So the dendrite goes on increasing, combining one dendrite to the other. In this particular diagram we have discussed. So the liquid form changing to dendrites, and the smallest dendrites forming largest dendrites, having several dendrites grown up, and then they combine, filling the gap between them one to the other, and finally forming a grain boundary. So this is the solidification of metal we have discussed. Later entered into the thermal equilibrium diagram, where the cooling curves, we have discussed about cooling curves at 0 degrees centigrade, liquid to solid, nothing but if we take the example of a pure water, then it forms ice. So that we have discussed in this particular diagram. When a graph is plotted between time and temperature at 0 degrees centigrade, the liquid phase changing to the solid phase, in between 0 degrees centigrade, liquid and solid are available. So after this discussion, we have entered into the cooling curve for different alloys having different points A and B. So these A and B points, we have studied that these are known as arrest points, and the temperatures at which they are marked are known as arrest temperatures. These are the arrest temperatures. And later discuss the cooling curve for a solid solution. This is the liquid phase and this is the solid phase. This is the phase changing start temperature, phase changing finishing temperature. And later discuss some points like lower critical temperature, LCT, upper critical temperature, UCT, melting temperature of alloy A, TA, melting temperature of alloy B, TB. Later discuss some more points about the phase diagrams and cooling curve of a solid solution, graph plotted between temperature and time. Later entered into the polymorphism. We have discussed that the polymorphism is a physical phenomenon where a material may have critical, more than one crystal structure. So the crystal structure, more than one crystal structure, if exists, that is known as polymorphism. Later discuss about the allotropy. So the material which has polymorphism, whatever the structure change, if it is reversible, then that polymorphic change is known as allotropy. So later discuss the cooling curve of a pure iron at different temperatures, what happens. We have discussed what is the alpha, delta and gamma irons we have discussed. So initially the BCC magnetic change to BCC non-magnetic, and then it becomes FCC non-magnetic, forming delta iron BCC. So this is the different changing of BCC to FCC and again BCC. So FCC, face-centered cubic structure, BCC, base-centered cubic structure. So this is the alpha iron, 1, 2, 3, 4, these are the ends. So this is the structure. And we have discussed the variation in microstructure and stales. So these are the several combinations. Austenite, this is the austenite plus ferrite. So austenite plus cementite, ferrite plus perlite, cementite plus perlite. So here starting with the austenite, 1.2% carbon dissolved in a FCC solution known as austenite. Later at 723 degrees centigrade, it's leaving the carbon changes to perlite here, and this 1.2% of carbon giving the steel layered structure known as perlite. So here 0 to 1600 degrees centigrade we have discussed, where at 0 to 910 degrees centigrade up to 910 degrees centigrade, iron is crystallized in BCC form known as alpha iron, which forms ferrite with carbon. And above 910 degrees centigrade up to 1390 degrees centigrade, 1390, it forms austenite with carbon known as gamma iron. And this again, whenever it goes on heating from 1390 degrees centigrade to 1600 degrees centigrade, it forms ferrite with carbon known as delta iron. So these are the different forms of iron, allotropic forms of iron. So whatever the we have discussed, so ferrite nothing but the alpha iron. It is stable below 912 degrees centigrade, having BCC structure. Only up to 0.02% carbon exists in solid solution. So this is the structure we have discussed of BCC, and this is one other diagram of BCC, unit cell diagram. Later austenite nothing but the gamma iron, which is having face-centered cubic structure, having high formability, high solubility of carbon. Over 2% of carbon can be dissolved in it. At 1148 degrees centigrade, most of the heat treatments begin in this particular phase. This is a face-centered cubic structure. Each phase has an atom in the center. So that's why it is known as face-centered cubic structure. So this is one other diagram. That is a unit cell diagram, delta iron. So at 1492 degrees centigrade, maximum carbon dissolved is 0.08%. So next discuss about cementite, which is nothing but iron carbide. So here we are discussing the austenite, FCC structure and the unit cell. So delta iron, cementite, nothing but the iron carbide we have discussed. Curie point, pearlite, composition of ferrite and cementite, and ladderite, composition of austenite and cementite. So having 4.3% carbon cooled below 1148 degrees centigrade. So below 723 degrees centigrade, ladderite changes to pearlite. So different iron carbon system compositions we have discussed. These are the diagrams having the compositions at phases, different phases. So with this, we are completing this particular presentation. Thank you.